Thank you so much for having me here. I'm pretty close. I'm just across the river at the engineering school. So I'm in computer science as my primary area, but my work is at the intersection between computer science and economics. So we often consider like incentives in many settings. And this work is kind of like inspired by that. So I call it data reliability scoring. So this work is a joint work with my graduate student Shi Feng and my collaborator Fang Yiyu at George Mason University, and also Paul Kattuman at the University of Cambridge. So what is the problem that we're talking about? So nowadays we all know that data is really, really important. So a natural question related to the importance of the data is the quality of the data, because we want high quality data. That's going to really help us to understand the information behind the data. But if we have low quality data, it makes the decision-making process extremely hard. But often data quality is questionable. So here are just some examples. So for example, during the pandemic, a lot of researchers, and including like government agencies, they are using COVID case numbers to make all sorts of predictions. And those predictions were informing the policy, like related to travel and related to medical resource allocation. But how reliable was the COVID case number? So there is a lot of evidence that the number that we collected may not be very accurate due to various reasons. And another example is that if you think about like a hospital has a lot of like diagnosis for its patient and then need to report the diagnosis in terms of some sort of code to the insurance company, there's all sorts of noise in that process. It could be just some reporting errors, or it could be some like intentional like up coding to report a diagnosis that's going to receive higher payment. And now if I think about the large amount of data that machine learning algorithms are used to train the models, there surprisingly is a scarcity of data because the models become really large and we really desire more and more data. And a lot of those data are crowdsourced. So crowdsourced by asking like online workers to label the data. And then there's also the question of, do they actually exert effort to label the data in the way that we expect them to do, or they're just to randomly give us some labels? So why this problem is difficult? So the problem is that we have data, and but we don't want any data. We want high quality data, or at least we want to understand what is the quality of the data that we have at hand. So this problem appears to be very challenging, mainly because of we have the data that we collected, but there is actually a ground truth, which is the quote unquote, the underlying true data. So what we really want is to understand whether the data that we collected is very close to the underlying true data. But the underlying true data is not observable. Oh, it's just too costly for us to observe. So that's make this problem challenging because data quality is comparing with a ground truth, but we don't have access to the ground truth. Then the question is, can we still do something here? So the reason that we think we're not just completely out of luck, it's possible for us to still do something, is for the following reason. So even if we don't directly have access to the unknown ground truths, which are the true data, we do have some observations that's related to the unknown ground truths. So for example, if we think that COVID case numbers may be misreported, the COVID mortality data are going to be more reliable because there is a very strict process reporting a patient's deaths. And that's going to lead to a more reliable data set. And there is some statistical relationship between the diagnosis of COVID and like the subsequent deaths related to COVID. And we do observe this, like the mortality data. And similarly, the reported diagnosis is something we have. The underlying true diagnosis, we don't know. But we do observe a lot of like medical test results, like image test or some blood test. And those test results outcomes are statistically related to the true state of the disease. And similarly, for the cross-house image labels, I think we don't really directly observe the correct label of an image, but we have the image. And there are some algorithms that we can apply on top of that image. So we can apply an encoder representation to have a succinct representation of the image. That's also related to the underlying ground truth. So what made us feel hopeful is even if we don't observe the underlying ground truth, we do observe some side information. And even if we don't know the exact relationship between what we observe and the underlying ground truth, we know that they're statistically related. So the question for us is whether we can typing into the unknown statistical relationship to be able to say something about the reliability of the data that we collected. So we try to initiate this research question. So clearly this is still a challenging question, and what we're trying to achieve may only be the initial results, but I think it's an important question because nowadays, whether it's data or whether it's like AI model outputs, we just don't have ground truth. We don't have access to the ground truth. So we have to leverage on other side information for us to gain confidence to what we have. So let me just abstract the problem that we will study. So what we're thinking about is that there is the underlying true data set. So we represent using X, which is what we don't have access to. This is the unknown. What we do observe are two things. One is the reported data set X hat, but the relationship between X and X hat, it could be that some noise was added, some mistakes was introduced, or some intentional manipulation were introduced during this reporting process. Okay? And then what we do have like observation on, what we do have access to is the outcome of another random variable, y. Okay? And what we know is that y has some statistical relationship with the true value of the x. So y is a statistical experiment, like based on x. But we don't know the exact relationship between y and x. So that's what we're hoping for, is that let's start with as few assumptions as possible. So we don't want to assume the knowledge that we know the statistical experiments, and we also don't want to assume the knowledge about like what we know about the potential manipulation. And we try to say, given the minimum assumption, what might be possible and what can we achieve? And I think admittedly, if we want to achieve more, we probably will need to know more about this process. But let's start from here. Okay, so then the question is, can we design a reliability score? And this reliability score takes the reported data set, because we want to assign a score to the data set, and what we can observe. So this is our observation. It doesn't depend on the true data. And we want this score to return a value such that it assigns a higher score in expectation to a data set X hat that's closer to X. So essentially we want to say that if X hat is very close to X, then we want this reliability scoring to assign a higher score compared with another data set X hat prime that is further away from X. So we kind of want this relationship. So that's the main question that we're trying to address. So what I'm going to do today is I want to formalize the problem of a reliability scoring. So this may not be a unique formalization, but this is how we currently think about the problem. So as part of that, I have been very weak about x hat is close to x. So in some sense, we need some way of expressing how far away a reported data set is from the underlying true data set. So as part of that, so we will say that, oh, there are some like reliability orderings for the data sets that we can consider. So we take those as examples. And then we introduce our reliability score, which is called Gram Determinant Score. So it is computing the Gram determinant of a matrix. So that's why it is called the Gram Determinant Score. So I will talk about the properties. So under what condition this Gram Determinant Score can preserve the underlying ordering of the data set. And I'll also try to give some geometric intuitions of why this score captures what we want. I'll very briefly touch on some of the experiments that we run on synthetic data and also on a machine learning data set that's an image label data set. Okay. So let me start it with the formalization of the problem. I think I already mentioned a lot. So basically, we're thinking about this picture. So we have the true data, the reported data set, and the observation. And all of them are considered as a data set of length n. So we're not considering time series data at this point. So really, we're thinking about the tabular data, and the order of the entries in the data set doesn't matter. So if we reorder one according to some permutation, we do the same for the other. So basically, for every element in the data set X, there is a corresponding reported element in the data set X hat, and there is also a corresponding reported, corresponding observation that we observed for Y. So these are the three parallel data sets. And then we say that we try to capture the relationship between the observation and the underlying true data set. So we capture that by saying that Y is a statistical experiment that relates to the true value of X. And this is captured by a matrix. So we call this matrix P. So this matrix P basically is saying that if there are three possible values of X, let's say that the possible values of X are 1, 2, and 3, then for each possible value of X, there is a distribution of Y. So there is a conditional distribution of the possible values of Y, and Y is drawn in according to that distribution. And that's a column in this matrix P. Okay. So the implicit assumption that we're making is that for different values of X, essentially Y are drawing according to potentially different distributions. Okay. And why this matrix P exists, but we don't know. So we do not require the knowledge of this matrix P. And let me just give a concrete example here. What does the random experiment mean? So suppose this is a miniature of our data set. The underlying true data only has two values, 1 and 2. So we only have like 5 data points. And we have a reported data set that's like some entries are different. So either being manipulated or it was due to some recording error. And then we have some observations Y corresponding to each data point. And in this case, the experiment may look like something like this. So basically, this column is saying, what's the distribution of Y when the corresponding X has true value of 1? So this is saying that, if the actual value of x is 1, then with probability half and half, we're either going to observe y to be A or B. And the second column is the distribution of y conditioned on when x equal to 2. So in this case, when x equal to 2, we will always observe y equal to A. So we will never observe y equal to 0. So again, I want to emphasize that this P matrix exists. This is characterizing the statistical experiment, but we do not have the knowledge of this P matrix. So at least at the end, we want to come up with a scoring method that doesn't require us to have the knowledge of this P matrix. So any questions so far? Very good. Okay, so I described so this model is actually really only have two types of relationship here. So I described the relationship between x and y. So now I want to describe the relationship between x and x hat. So the subtlety here is that for y, it is a random variable that depends on the true value of x. But we're actually not assuming x is a random variable. We're assuming x is a realized data set. And consider any other possible reported data set. So how do we describe the relationship between x and x hat? So we characterize the relationship between x and hat using a misreport matrix. So the misreport matrix will have entry, so the entry at the ith row and jth column, basically saying that the percentage of the data that actually has true value equal to I, but the reported value equal to J. So let me get closer to this. So what does it mean? So this misreport matrix basically captures how the true value of X were manipulated in X hat. So it captures the frequency of that. So for this particular example, because if you notice that for all the true value of X equal to 1, 2 of the reported value of X hat still equal to 1, but 1 becomes 2. Right? And for the true value, so Q is the row matrix. So that means out of the 5 data points, there are 2 data points where the true value is 1 and the reported value is also 1. So that's the first entry here. And the second entry is out of the all data points, what's the fraction of the data point that has true value equal to 1 and the reported value to be equal to 2? And similarly for the second row. So notice that this is essentially the joint frequency of the true data X and reported data X hat. And such a matrix exists between any pair of X and X hat, even if we don't know what this matrix looks like. So we're just trying to use the Q to capture the structure. Okay, and then we can also have the conditional, like the manipulation matrix, essentially saying that the frequency of the reported data X hat conditioned on the true data. This can be viewed as a manipulation strategy that's generating the data set X hat from the underlying true data X. So what it is saying is that condition on the true data value equal to X equal to 1, then 2 out of the 3 points, or 2/3 of those data actually has a reported value of 1. So we have this 3 data, and 2 of them has a reported value of 1, and 1 of them has reported value of 2. So this is the manipulation. Okay. And then we can also capture kind of like the frequency of the true data. Like we use a matrix to represent that, just for like manipulation. Well, I guess the operational, like a benefit of using matrix multiplication, but only the diagonal elements matters here, and all the off-diagonal elements are 0. So this basically captures, like out of the 5 data points that we have, 3 of them has true value of 1, and out of the 5 data points that we have, 2 of them has a true value of 1. So these 3 matrices is actually even if we only have 1, it helps us to capture the relationship between x and x hat. And what's the relationship between the 3 matrices? So the joint frequency of x and x hat equal to the frequency of x times the transpose of the manipulation matrix. So this is not difficult to say. And the important quantities that we care about is the joint distribution of y and the reported data x hat is just equal to p times q. Okay. And this can be decomposed using like the expression of q into p times qx and times the transpose of this matrix. And the joint distribution of y and the true data, which is this one, it's just a p times qx. And let me put back the figure. So the relationship between y and x are determined by p. Hence, the joint distribution of the true x and y is p times the frequency matrix of x, which is qx. Okay. And notice that ideally, we really want to know this distribution, right? But we don't really observe the underlying true x, so we don't observe that. And then the relationship between x and x hat is through this conditional matrix. So this is essentially the manipulation strategy. So x hat is generated through this matrix. So the joint distribution of x hat and y is the multiplication of this 3 matrix with this matrix taking the transpose, because the way we set it up. Okay. So I think this is, I didn't introduce anything new. This is really just the basic setup. But what we want to do is really understand the structure behind what we can observe and what we do not observe. Because our hope is what we can observe are the distribution of x hat and y, right? So in some sense, what we can possibly observe if we have enough data will be this p times q. And what we want to achieve is we want to extract information from this p times q such that we can tell apart whether this manipulation matrix leads to very big deviation or not. Because ideally, we want them to just give us this. So we want the joint distribution of x hat and y to just be p times qx. Okay, so that's the setup. And I mentioned that what we want to achieve is that we want our reliability score to assign a higher value in expectation for data set x hat that's close to x. So then we have to be able to say something about when we consider a data set x hat is closer to x. There are any, like you probably can have your own practical like requirement about what you consider a data set is of higher quality. Here we just give you some examples. So for example, if I just care about whether I get exactly true underlying data set, so we call this exact match ordering. So what it says is that I want our reliability. So the data set ordering is basically saying that only the true data set is considered to be ranked highest compared with any manipulated data set. So this is saying that if x hat equal to the true data set, but x prime doesn't equal to the true data set, we want to make sure that x hat is strictly ranked higher than x prime. So that's very extreme, right? And then this basically says that x hat, there's no manipulation at all, but any other data set x prime that has manipulation, because when there's no manipulation, the Q matrix is just the identity matrix. And the second one is from the Blackwell ordering. So this is very natural of thinking that if we have a data set x hat, and then if we start from that data set and start to add random noise to generate another data set x hat prime, then we want, so this data set, because this is a garbling process of the original data set x hat. So I want to make sure that the ordering says that x hat is of higher quality than x hat prime. And this is just the Blackwell ordering, I think, proposed back in 1950s. And what this means is that, if x hat prime is a garbling of x hat, then the Q matrix associated with x hat prime, denoted as Q prime, equal to the Q matrix associated with x hat times a column stochastic matrix, because that's the garbling process. So there exists some matrix T such that this is a column stochastic matrix. Oh, we can also think about the Hamming distance. So basically, how many elements in the x hat are different from those elements in the true data x, and rank the data set according to that. And this also can be represented in terms of the property of the Q matrix. That's why we like to work with the Q matrix, because the reliability ordering can be represented as properties of the Q matrix. Because the Q matrix, the diagonal matrices, are the data that are truthfully reported. Any off-diagonal matrices, elements in the matrix are like misreported data, the percentage of the misreported data. So the Hamming ordering basically says that if a data set, when we represent that using the matrix Q, has a trace that's greater than the trace of another data set, then it should be considered as higher quality. So these are just some possible considerations of how we think about the data set quality. So we're not claiming that these are the only ones that you should consider. Oh, these should be the ones that you consider. But I think these are the ones that we try to work with, and we're able to show whether it's possible to or impossible to achieve this. Okay, so now I can formally state what our goal is. So our goal is to, we want to score to preserve the reliability ordering. So basically saying that, suppose you care about a particular reliability ordering, could be one of the three that I talked about. We ask the question whether we can design a reliability score S, such that when the score, assign a value to x hat, a data set x hat, based on the observation y, in expectation, this score is going to be higher compared with what the score assigned to another data set x hat prime and using observation y. When x hat is ranked higher than x hat prime according to the reliability ordering that we care about. So essentially, we want to say that our scoring function will be able to preserve the underlying data set ordering that we care about. And we don't know whether this is possible or not. and to what degree it is possible. So that's what we try to find out. Okay. So are you good with the setup so far? Okay. So now let me introduce our Gram Determinant Score. So what are we doing? So I want to first introduce the score as if we know the knowledge of P and Q. Because at the end, and then because that allows us to easily prove what properties this Gram Determinant Score can achieve. And then we're going to find ways to estimate this score and say that like it preserves the properties that we have approved. Okay. So I will introduce the Gram Determinant Score first. I'll talk about the properties and also like talk about very briefly that the impossibility results. And then I think what's most interesting is that I want to give some geometric intuition of why the Gram Determinant Score actually captures what we hope to capture in measuring reliability. So let me dive in. Okay. So Gram Determinant Score. So the only thing we can observe empirically is the joint distribution of x hat and y. And I think as I explained in the model, the joint distribution of x hat and y is P times Q. So the product of the matrix P, which is our random experiments that relates y with the true x, and the mystery part matrix Q. So we start by assuming, let's just assume that we know this P and Q, because if we have large enough data, the empirical frequency that we observed for x hat and y will approximate this P and Q very accurately. And if we can't even do anything, when we have the knowledge of P and Q, we probably can do very little when we only observe the empirical frequency from x hat and y. So that's why we're starting with this. So, but we're going to eventually not using this, but bear with me. So I want to explain the properties of what we defined, assuming the knowledge of P and Q. Okay. So suppose that we know P and Q. So P and Q is also a matrix. And for matrix, we can think about the columns of the matrix and then the shape that's spanned by those columns. And there is a notion of volume for that. And if the matrix is a square matrix, we can just directly calculate the determinant of the matrix. And that's that's a volume spanned by the columns of the matrix. But P and Q is not necessarily a square matrix. So we need to consider a generalized version, calculating the determinant of what's called a Gram matrix. So the Gram matrix is basically saying that, oh, I take the original matrix, and then I left multiply the transpose of the original matrix, such that this matrix J hat is guaranteed to be a square matrix. And it's also, we can calculate the determinant. Okay. So our reliability score is basically saying that, let me take this PQ matrix and I calculate the gram determinant of this PQ matrix. Okay. So this may sound like why we're doing this. This doesn't seem to have intuition, but I'll get back and explain why the volume is actually a very good way for us to think about how far away x hat is from x. So this is our score. And with this score, what does it capture is that the PQ matrix is the matrix. And this matrix has the column, right? And if the columns of the matrix are represented as the vectors in the space. Then the parallelepiped, I never can pronounce this, but basically it's the shape capturing the span of this matrix. It's a shape in the space, and it has a volume. And the volume is basically shaded in the blue. So essentially what we're trying to capture is we want to use the volume to measure the reliability of a data set. So what properties that it has? That this Gram Determinant Score can preserve or approximately preserve the three reliability ordering that we talked about under certain conditions. So we still need conditions on what the experiments looks like and what the Q matrix looks like. But what I want to, so these are not that important, but what I want to highlight are that we do need the experiments to be independent. So what does it mean? It means that the columns of the matrix P needs to be linearly independent. So the distribution of Y, like condition on different values of X, needs to be linearly independent. So that's the requirement here. And the second is that, so this is actually a very minor requirement. This is basically saying that the misreport matrix is not just a permutation matrix. It's not just a relabeling. And this one is slightly stronger if we want to really achieve the black-white ordering as a strict ordering. So this would require that the true report is the mode of the misreport for any value, meaning that it has the highest value. And for Hamming ordering, we can only achieve approximate Hamming ordering for balanced data. So while this may seem that we are enforcing some restrictions on P and Q, but I want to argue that it's because the problem is really challenging and we are trying to make minimal assumptions about our knowledge about P and Q. So in fact, we have almost matching impossibility results, basically saying that for any reliability scoring function that you can imagine, if these conditions are not satisfied, it's impossible to preserve the corresponding data reliability ordering. And I think what people really care about most is the independent experiment. So meaning that the relationship between Y and X is a statistical experiment. We want that statistical experiment to be having linearly independent columns. And one can argue that we can use any Y. So it doesn't have to be a fixed Y. We can even have multiple different Ys with the hope that one of them will satisfy the P dependent.
So if you don't have this independence hypothesis, so I think of that as like P is like crushing some information down, like from X down to Y, is the failure of your ordering preservation, does it actually get things in the flipped order, or is it just that things are equal when you want one to be strictly larger than the other?
Right, that's a really great question. So I think, so you can imagine that when we don't have linearly independent, so basically think about the extreme case that—
It's constant, right? If we're just the same.
Like two possible values of X have the exact same distribution of Y. So which means that we really do not have information to tell apart what X is. If people just misreport between these two, there's no way we can tell apart whether that's a misreport or it's truthful reporting, because we assume no knowledge about X. And at the technical level, what it means for our Gram Determinant Score when P doesn't satisfy the linear independence condition is that our Gram Determinant Score is going to be 0. So the volume in the current dimensional space is 0 because we are thinking about whether it's possible in that case to reduce the dimension and think about the volume in a lower dimension. But that's ongoing effort. So I don't have, yeah, thank you. So, okay. Another really nice property with the Gram Determinant Score is that it's experiment agnostic. Because I was thinking about that, we're picking a y. Y is just stochastically related to our true data x. We really want our reliability ordering to remain to be the same, regardless of which y we selected, as long as the experiments associated with the different y are all linearly independent. So that's what we call the experiment agnostic. So basically saying that the ranking of the data set according to our reliability score doesn't depend on the y that we choose. And it turns out that Gram Determinant Score satisfies this property. And in some sense, it is a unique score that satisfies this property. So up to some scaling. Okay. So that makes this to be very desirable theoretically. Okay, so now let me get to talk about why the Gram Determinant Score gave what we want. So essentially, ideally, whenever one truthfully report their data, meaning when x hat equal to x, so whenever a single data point was truthfully reported, the observed distribution of x hat and y will be the true joint distribution of x and y. So which is just the product of the matrix P times QX. So this is the joint distribution of x and y. Okay? And this is what we hope, that the highest quality of the data is going to lead to a distribution that equal to P times QX. Okay. And when people do manipulate, we're essentially adding this manipulation. So we're multiplying this manipulation to the product of P and QX. So that gives us the product of P and Q, which is the joint distribution between x hat, so manipulated x hat, and y. And this is something that we can empirically observe if we have enough data, right? And this is not something that we can observe, okay? Since we're using the volume of the space spanned by the columns of the matrix as our reliability score, so the property that we want is when the manipulation is large, the volume shrinks further. And now if we look at what this means. So when we have the matrix PQX, so these are the column vectors of this matrix, and the light blue shaded region is capturing the volume of that space. That ideally is the highest volume that we can possibly have, right? So this is the highest score that for the most accurate data set, okay? But when agents start or people introduce error or start to manipulate the reported data, we're right multiplying this matrix. So this is Q is a column stochastic matrix, and this is a transpose of that, so which is a row stochastic matrix. But what's interesting is that under the linear independent condition of P, the volume of this is exactly equal to as if we drop the transpose. So we're multiplying a column stochastic matrix. And when we're multiplying a column stochastic matrix to the original matrix PQX, essentially what we're doing is that the new column are linear combination or convex combinations of the old columns here. So essentially, all these new red vectors are convex combinations of the original red vectors on the left. Because it's convex combination, it can only lie inside the original space. So essentially, all these red vectors are inside of this original space. And now if I'm measuring the volume spanned by these new vectors, the volume decreases. So that's the intuition why we're using the Gram Determinant Score. Measuring the volume of this matrix can give us a reliability ordering. Because data manipulation will lead the columns of this matrix to move inside, and hence decreasing the volume that we measure. So that means that truth value report, x hat equal to x, will have the highest score according to Gram Determinant scoring. And any manipulation will have lower score. So that satisfies the exact exact ordering of the data sets. And then Blackwell ordering basically saying that if I multiply a Q by another stochastic matrix that is adding additional noise, that will only make the volume to shrink further. So that's the intuition of why we have this Gram Determinant Score. Okay. So I think estimating Gram Determinant Score is not it's not hard, but I want to because essentially what we can do is we do observe the frequency of x hat and y, and if the size of our data is large enough, that frequency is a good estimator of the joint distribution of x hat and y. But I also want to give some intuition of what are the elements in this Gram Determinant matrix. Because remember that we first calculate this Gram Determinant matrix, and then the Gram Determinant Score is the determinant of that matrix. And this Gram Determinant matrix actually captures the relationship between x hat and y. So why is that? Because every element of this matrix is essentially giving the value of the expected probability for two data points have the same value y. So they agree on y when these two data points, when the reported data points are x and x prime respectively. So if we look at an element at row x, so corresponding to the true value of x, the reported value of, corresponding to that a reported value of x, and the column x prime also corresponding to a reported value of x prime. And then this element in this Gram Determinant matrix captures that, oh, if we have a data point that has a reported value of x, and another data point has a reported value of x prime, what's the probability that their associated y actually has the same value? So this is the probability of agreement under a fixed manipulation strategy. So that's what this matrix is capturing. And we do observe the empirical agreement from the data, so from the x hat and y. So that's why we can just naively take that and do the estimation. So I guess one thing is that we can just use the empirical frequency to calculate the Gram Determinant matrix, and then apply calculating the determinant and use that as our reliability score. So this is consistent as the number of data points that we have becomes really large. A more subtle one is that we can actually try to decrease the bias by a careful design sampling procedure. So we have another estimator that I'm not giving the details. That way, we can guarantee that the Gram Determinant Score satisfy all our reliability ordering result with a finite number of sample, because this is a asymptotic result here. Okay, yeah, so these estimators, they do preserve the same reliability ordering that we introduced early on. Okay. So far, we analyzed or we designed the Gram Determinant Score for a finite value space of X and a finite value space of Y. So essentially, our possible values of our data is a finite set, and the possible values of our observation is also a finite set. So we can generalize the Gram Determinant Score by using kernels. And in this way, we will be able to deal with the continuous space of Y. And I also want to emphasize that in this setup, the space of Y can be drastically different from the space of X. So we really don't require that the space of X and the space of Y to have any particular relationship. So the kernelized Gram Determinant Score basically is like applying a kernel function that we have, such that like we redefine our new kernelized Gram determinant matrix, and then calculate the determinant of that. And a lot of kernels will preserve the same data reliability ordering that we have proved before. Okay, so I think that's the part that we designed one reliability score, and it seems to be having some desirable properties under conditions that's almost matching the impossibility result that we proved. And it has a geometric interpretation. So we ran some experiments trying to understand how our method works on some synthetic data and also on an image data set that's very well known in machine learning. So let me just quickly show you the result that we had. So what we did here is that we create a synthetic data set and treat that as the underlying true data set. And we run this for like, I think 10,000 times. And then we also sample a statistical experiment, sample a matrix P, to create an observation Y associated with the true data set. And then we create a sequence of like reported data set by introducing error or manipulation in different ways. So I think the blue one is just we introduce random error to create the X hat, and we can increase the probability of introducing an error to create data set with degrading quality. And then we also consider some like systematic manipulation strategy. So for example, I will always over-report. I will never like under-report. And then we increase the probability of over-report. So basically what we're doing is that we tried a bunch of ways of like introducing the differences between X hat and X. And we also control how much like manipulation or noise we're adding, such that for any single method, we have like a sequence of data set with degrading quality. And then we apply our Gram Determinant Score to those data sets, trying to measure the reliability. So the x-axis is our score. And then, so different data sets score differently. So essentially, this is showing our score to be increasing. And since our theoretical proof only shows that we can only preserve the Hamming distance ordering approximately, we actually measure the actual Hamming distance between the data set X hat and X. And this is a figure. So essentially, for all the experiments that we've done, if our reliability score is high, the corresponding Hamming distance between x hat and x is low. So which essentially saying that empirically, it actually perfectly preserved the data reliability according to Hamming distance in our experiment. And we also tried some other distance metric to measure x and x hat, because we have nothing about, for example, measuring the distance between x and x hat using L2 norm. When we measure the distance using L2 norm in our experiment, we see a similar trend. So it's basically when our reliability scoring gives a higher score, then the data set is closer to the underlying true data set according to the L2 norm. So that's for the synthetic data. And we did something similar for the image label data, but I'm only plotting the one that we're introducing random noise. But essentially, we did the same as the previous one, and the trend remains to be the same. But let me explain what we're doing here. So this is a very well-known image data set with the label. So this is considered to be this data set is used for supervised learning. So this is considered to be a data set with the correct label. And then we manipulate the label to create different reported data set. So we did all sorts of different manipulation to degrade the quality of the data. But then what is the Y? What is the natural Y in this setting? So we actually used an embedding encoder function to take the original image and create a mapping to a different space. And because the algorithm is fixed, and the algorithm also has some randomness, so we're using the embedding as our Y. And then we evaluate the manipulated data set X hat using the embedding Y to calculate our Gram Determinant Score. And again, we measure the Hamming distance and also the L2 norm. As you can see that the trend keeps the same, that when we're having a higher score, the distance between the true data set and the reported data set is small. So it's showing that it at least captures the reliability in some sense. Okay, so I want to say something about the related work. So this work is actually inspired by the paper here, which is an economic mechanism. It's called a pure prediction mechanism that was designed to try to incentivize an individual to truthfully report their information. So this is a setting about reporting their private information. And I think the intuition that we get, and hopefully you already get from our method, is that what we're essentially using is an information theoretic approach. Because the decreasing of the volume after some manipulation is basically saying that when you do post-processing of the data, it can only decrease the information. And the volume actually satisfies some notion of mutual information. So we're essentially capturing the mutual information between X hat and Y. And when people do manipulation, because without manipulation, we're capturing the mutual information between X and Y. With the manipulation, X hat is a post-processing of X that can only decrease the mutual information. So that's what the volume comes into play. And this paper gives information theoretic a view of the elicitation problem, and we really got inspired by this work. Okay, so far so good, right? So it seems that our model is doesn't require a lot of assumptions, and we're able to say something theoretically to rank the data set. And empirically, it also seems to be that the ranking preserves the data set ranking relatively well. We should be happy about it. But there are something that we're unhappy about it. And I think it's going to be interesting future work. I think one observation is that we can only rank reported data set with respect to an underlying true data set. So think about that. You have a true data set that's like labeled image, which we don't observe. And each of you get a reported version of that. This reliability scoring will be able to alter that. But we can't compare the quality of the data set when their underlying true data set is different. And this is also because if we only have one data set, I can't really interpret what the score means. If the score says 100, I don't know whether that means high quality or low quality. So the absolute value of the score doesn't have a very natural interpretation. So we can't really make the decision of saying that let's apply this scoring method, and if the score is higher than 100, the data is of good enough quality and we can use it. So ideally, we want to have something like that, but we haven't achieved that yet. And I think that will be an interesting open question. Let me stop here. Thank you so much.